the others are coming in. I think we have gone through quite a lot these past 3 weeks, right? All right, so this is week 4. And this year's exam diet starts on the 3rd of December. Okay, so we received the dates for the exam. It starts on the 3rd of December, which is the Monday after week 11. Yeah, so theoretically it's possible, let me just remind you, it's possible that you finish all the way to the Friday of week 11, you get Saturday, Sunday off, and then the exam is on Monday. It's possible, right? So of course we will try, it does our exam schedule, but there's only so much we can do, especially if the exam is timed to run at the same time in Glasgow. All right. There are also cases whereby, take for instance, like we might try to have you complete the lectures slightly earlier, and of course, then your exam is the first day, the exam diet. But any day in the exam diet is possible for us to hold an exam, because that's what the exam diet is for. All right. So let me just remind you that for December, the exam diet starts on the 3rd of December, which is the Monday after week 11. Okay? All right, so before we recap on where we finished last week, so this is week 4. All right, let me just go through some simple simulations with you. Okay, so I can't seem to read this very well. And I believe neither can you, okay? But what we have here on the screen is a simulation. All right, so this is a MATLAB and Simulink simulation. Okay, so most of you would use this software, for basic modeling and simulation in your final year project. Okay, so here we have an input. I suppose by now you guys know what an input is. So it's the signal that goes into the system. Okay, we have the actual model, which is a non-linear pendulum model at the bottom. Okay, and if you remember from week 2 of our lectures, we said that we can linearize such a pendulum model. So if you assume a small angle sine theta is theta, then you can derive a second order transfer function. Okay, so the whole objective of this simulation is to show you that, yes, the linearized model is quite close to the actual model itself. All right, so there's an animation here of a pendulum with a pivot point. Okay, so you can see this is a typical response of a second order system. All right, so it goes to a certain value, it oscillates around that value. There is no closed loop here because it's just a simple pulse input and a simple output, right? So you get to the angle. It's not very well controlled, you can tell, right? So you don't really want a control system like this. Or do you like a control system like this? I don't think so, right? So if you imagine now we're talking about Industry 4.0, and you have a robotic gripper that does pick and place. Okay, so it picks a chip up and supposed to place it on the microcontroller board. So it goes pick, then it goes, so you can never actually insert the pin properly onto the microcontroller board. Okay, so this is out. All right, we don't like this. Okay, the other thing that I just want to point out to you guys, I'm not sure if I get the simulation running properly, is that once you have derived that, did I actually show you that the linearized and the non-linearized models are close to each other? So, sorry about that. Okay, let me run this again. All right, so if we look at the outputs of the linearized model and the output of the non-linear model, they go to a bus, which are all both plotted on the scope. Okay, so if you look at this scope, of course, you can't see it very well, but there's a rectangular house. On top, there's the input. On the output, there's a blue and yellow line. So one of it is the linearized output. The other is the non-linear output. And you can see that they're actually very, very close. All right, so it's okay in this sense to linearize the model. All right, so with a linearized model, we can then proceed to check if open loop and closed loop would help for this particular scenario. So okay, so in this case, I have another model here. You can see a transfer function, which is in the green block. Can't read it very well, but it's a standard second order. And there is actually no feedback, you'll realize, because there's nothing going back to the reference here. All right, so this is entirely open loop. All right, we can run it. So this is how you work in open loop with a simple pulse. Very, very bad. Okay, not something that we like. Okay, so let's say if we apply some feedback. Bear with me, I'm not sure if this will work properly. But here you can see that that's the linearized transfer function. You can see here that we are taking the output y, that we are measuring the variable y. We're taking this, and we are adding some noise to this output before feeding it back to the reference. Okay, and here you actually do see that before we take this output y, we've also added another disturbance signal. Okay, and let's see how this would work. So of course we have applied some gain here, which is controller C. Gain C. Let's run this. Oops. Yep, this is what I mean. Okay, but before we proceed, just bear in mind that the controller gain C is, in this case, we have applied just a simple proportional control. So with a very basic and limited control system, this is what we get. Okay, slightly better. All right, not as bad as when it was fully open. Okay. All right, so at least for up to a certain period of time, it was oscillating in a very, very small range. All right, and that's when you can actually do the insert. Okay. All right. Okay, so there are actually some more that I want to show you, but let's do that maybe later. Okay, so back to where we left off last week. All right, so where we were, we talked about design issues. Okay, so if you have a pen, I said the last time, put a star on this, because some of the typical concepts that we'll try to test is whether you understand what your design targets are and what are the limitations, okay, as to how you can achieve your design targets. All right? Okay, so if that is clear, this is where we are. We went through half of this, and we're going to move on to the more mathematical style. Okay, which was the reason why I gave you that simulation to, in a way, ease your brain a little bit. All right, in case it's just too much for you to handle. All right, so we were here. For those who are still trying to search channels, we were here. And we have covered basically everything except now that we have last finished measurement noise, so we're going to move on to plant capacity. Okay, and then we'll come back to talk a little bit about robustness. All right, okay, so where we left off from last week, we finished stability, the transfer function, we finished disturbance attenuation, and measurement noise, good command response, those we have done last week. Now we're moving on to plant capacity, and we'll talk about robustness, okay? All right, so now that you found your stack of notes, all right, this is where we last left off. All right, okay, so for us to be able to understand plant capacity, there is yet another transfer function that we want you to know about, which is what we call the control sensitivity function. All right, and that's SU for short. So you will realize that we have purposely left out the denominator here, so you guys can fill in and hopefully stay awake. So there's an empty missing denominator in your notes that you should fill in. There are some handwritten stuff that you can write down as well. Basically what we want to do is to say, if I want to study the limitation of plant capacity, what is going into my plant? All right, so you can see here that you have an output of the controller U that is being fed into your plant directly. All right, Okay, so if you're asking for too high a control output here, so if your U is very high, like 1 million amperes, which is not possible, then of course your plant will not be able to deliver that kind of performance in response to your input, because there's a limitation on the plant capacity. Okay, so for you to be able to understand that, let's have a look at what this control output signal is. Okay, so basically, if you read the block diagram, you have the control signal, which is U, and U is really C times E, where E is the error between your reference R and your output Y. Not forgetting that you have a measurement noise. Okay, so basically U is C times E, and what is E? E is the filter reference, which is FR, minus your measurement noise N, that's over here, and your output Y, which is over here. Alright, and we had derived your output Y previously, okay, which is T times FR plus S times T minus T times N. Okay, and the next question is, of course, how do I actually derive U to be in this format? Alright, so there's two ways I can teach here. I can tell you that, hey, please go home and derive it yourself. Okay, or I could give you an example of how you can derive this, and then, hey, please make sure you go home and revise it again. Alright, so that's what I'm going to do now. So let me just take this away. And as part of the revision, if you could just, write down the steps, I think will be helpful. Hopefully you can have a better, material retention, by week 12. Okay, so the first thing that we spoke about is, if you want to know what your control output is, so that is U. Alright, and what is that? That is simply your controller times the error E. Okay, and we know that this is none other than C bracket. What is error? Error is a filter reference minus the measurement noise minus the output. Okay, and so this will give you C FR minus N. And what is output Y? Output Y is minus T. Okay, let me just write down CP naught over 1 plus CP naught, the filter reference, minus 1 over 1 plus CP naught times the disturbance plus CP naught over 1 plus CP naught times measurement noise N. Okay, so that's your output Y that you substitute into the equation. Alright, so once you are done, you see that really you have N here, FR here, and FR here. Okay, so it makes sense to try to simplify. Okay, so to simplify, C, and then next thing is you have 1 FR, so 1 minus CP naught over 1 plus CP naught will just give you 1 over 1 plus CP. And so you take this minus this. Okay? And then of course there's 2 N here, one measurement noise N here, and another measurement noise N here. So this is minus 1 plus CP naught over 1 plus CP naught. So this will give you minus 1 over 1 plus CP naught times N. Okay, you take this and you take this. Alright, and then you only have one last term left for disturbance. So just bring it down. So that is minus 1 over 1 plus CP naught times D. Okay, slow and steady and you don't make any mistakes. So you see that they have common factors. Very simple, just take the common factor out of the equation. Alright, so you end up with C over 1 plus CP naught, the filter reference minus the measurement noise minus the disturbance. Okay? Alright? And this is what we call SU, the control sensitivity function. Okay? All right. Why is SU important? All right, so now that we know that SU is basically C over 1 plus Cp naught, you can now analyze the characteristics of plant capacity. Okay, so you can check that in your notes, all right, there's a blank here for denominator, and it should be 1 plus Cp naught. So your control sensitivity function SU is C over 1 plus Cp naught. Okay, for those who just came in, there is a blank in your lecture notes that you should try to fill in. So find out from your classmates what it should be. Okay, all right, so before we move on, any further questions? No? Good. All right, so next we move on to plant capacity. So SU, why is it important? All right, so here we say that, we have derived that SU, which is the plant control sensitivity function, is C over 1 plus Cp naught. All right, and bear in mind that, your complementary sensitivity function is Cp naught over 1 plus Cp naught. So basically, T, which is your complementary sensitivity function, is your control sensitivity function times a plant. Okay, so any requirement on your control sensitivity function can be translated directly into requirements for T. Okay, and what does T do? T affects how well your reference follows your output. Because Y, output Y is T times FR. Okay? Alright? And of course, output Y is minus T times measurement noise as well. Okay? So first thing that we want to understand is if you want to prevent inputs that are too large because of limitation on plant capacity, your SU should not be too large. Because if you have a very large SU, then you have a very large control output, U. Okay? And the next thing is, of course, if SU is related to T, so we know that at low frequencies, the loop gain L should be high for low sensitivity, S, and the magnitude of T is close to 1, as shown in the plot here. So if at low frequencies T is very close to 1, all right, and T is related to SU times P, okay, meaning your SU is actually very high. So this can lead to plant capacity being exceeded. Okay, and the other thing is, of course, we know that at high frequencies above the bandwidth, T drops. So we understand that, of course, SU should also decrease as fast as possible. Otherwise, you end up with a very large T above the bandwidth, which is totally not necessary. All right, because you only operate from omega equals to 0 to B, which is the bandwidth. All right, and in this range, you would like T to be high because only when T is high, Y equals to T times FR, your output Y will follow your filtered reference FR. Okay, but above the bandwidth, do you still need T to be high? Above the bandwidth, your system is no longer operating in that frequency, so there's no need for T to be high, and in actual fact, you want T to drop as fast as possible. So you want SU to drop as fast as possible as well. Okay, and how do you influence this part? You influence this part in your controller design, C. Okay, because T is Cp naught over 1 plus Cp naught, and SU is C over 1 plus Cp naught. Okay, so we want it to drop as fast as possible beyond after the bandwidth, so as not to have the measurement noise affecting the input. Okay, so just understand that. All right, so this is how plant capacity is related to the complementary sensitivity function. The next thing that we need you to understand is that, what is SU? SU is C over 1 plus Cp naught. It's really taking the complementary sensitivity T, dividing it by P. Okay, so SU is T times 1 over P. So it leads you to think that, well, if your loop gain, okay, especially for first order transfer functions, which are effectively low pass, if your loop gain, which is Cp, is very, very high, then SU is approximately equals to 1 over P, because your T, when your loop gain is very high, your T, which is L over 1 plus L, then is approximately L over L. Because if your loop gain is very high, if L is very large, 1 doesn't make any difference. Okay, so if L is large, your denominator of 1 plus L is simply L. And you end up with L over L. So that is approximately 1. Okay, so under this situation, T is approximately 1. So of course, SU is T times 1 over P. Your SU is just 1 over P. What is P? P is your plant. Okay? And we say that, well, if you are lucky and your project manager says, hey, control this. And this, which is your plant P, has zeros in the right-hand plane. Okay, so an example is over here. So if P is K times S minus 1 over S minus 1 times S minus 2. So this has an unstable 0, which is S equals to 1. Okay, and what is 1 over P? 1 over P will then now have an unstable pole of S equals to 1. Okay, so if your P has zeros, they are unstable, and in the right-hand plane, 1 over P has an unstable pole. Okay, and 1 over P is then unstable. All right, so if that's the case, what do you do? How do you control? Can you still control this? Of course, because otherwise there will be no longer any more jobs for control designers. All right, so we can control this, yes, but just understand that SU can only be made equal to 1 over P up to a frequency which equals the magnitude of the plant right-hand zero of the smallest amplitude. So what is this trying to say? Okay, basically we are going to tell our project manager that yes, sir, I can control this, but okay, we will have to limit the frequency of the system. All right, so how are we going to limit the frequency? I'm going to tell you that the range of frequencies that you can operate in, omega, is only going to be from 0 to B. And what is B? B is my bandwidth. And what is this? This is going to be less than the smallest right-hand plane 0 of my plant, because SU is 1 over P. And this smallest right-hand plane 0 of P is your smallest unstable hole in 1 over P. Okay? So yes, you can control this, with something with an unstable right-hand plane 0. But because the control sensitivity function, at high loop gain is approximately 1 over P, so this unstable 0 in your plant is now an unstable pole in 1 over P. So your control is only possible if you limit the range of frequencies omega to 0 to B, where B is less than that of the smallest right-hand plane 0. Okay? Alright, so as control designers, we get away with a lot of things. But of course, sometimes we get very angry, with mechanical designers, not you guys, but people who only look at the hardware, which is the reason why you are doing a control course. Okay, so you don't just look at the hardware specifications. Reason being, if you go and design something that comes with a certain mass, that comes with a certain stiffness, that comes with a certain damping, and it comes in a way such that the zeros and the poles are unstable. What do you expect the control engineer to do, How do I control your hardware which is now really unstable? Alright, so all we can do really, but we are proud of what we do, is the ability to actually produce a system that meets the design specifications up to a certain frequency. Okay? Alright? Next, what we want to discuss, of course, now that we have finished plant capacity, is how robust your system can be. Alright? So we have done this before. This is just a recap. Alright, so here what we are saying is, in terms of robustness, a quick summary, that if you have loop gain perturbations, that's your delta L, okay, relating to your Doyle's stability criterion. Okay, so if you have a nominal loop L naught, fresh out of the factory. Over time, when wear and tear, it became L, so it's shifted. All right, so the change between L to L naught is what we call delta L. All right, and from Dawes stability criterion, we say that if the system is robust, the delta perturbation must be less than 1 over T. Okay, and that's the maximum T that you can find. So this must be less than that. All right, and then for inverse loop gain, so if my loop L has shifted, my inverse loop, that is 1 over L naught, has now shifted to 1 over L. Okay, and if you take the difference of these two, you end up with an inverse loop gain perturbation, and that is what we call delta L inverse. All right, and we have proven that this must be less than 1 over the sensitivity function. Okay, so basically what we have concluded is if this two is true, then of course, in terms of the performance, we all already know that at high frequencies T must be small on the graph, and low frequencies S must be small. So at high frequencies, measurement noise is attenuated over here, and low frequency disturbance is attenuated over here. The system only works from 0 to B. Okay, that's the range of omega. All right, and what are the perturbations that are allowed? So here we tell you that because the magnitude of delta is less than 1 over T, and T is very low in high frequency. So if you have uncertainty at high frequencies, which is the left-hand side, and your T is actually very low over here, so these high frequency uncertainties, if they exist, this might cause very significant loop perturbations. All right. So similarly for the second case, if you look at the inverse loop gain perturbation, which is related to 1 over S, okay, and S is actually small at low frequency. So if you have low frequency uncertainty, which reflects in S, this can cause significant inverse loop gain perturbation, and that relates to this equation over here. All right, so this is just a quick summary. And then the other point that we wanted to bring out is that there exists then, of course, a crossover region where your loop gain is approximately 1, very close to your critical point. Okay, and in this region, just note that neither S nor T can be small, and we really need to prevent them from peaking. So how do you do that? That relates to your SM and your RM, which are the stability margins for your loop and your inverse loop. Okay? All right, so we have gone through this. If you are asked in the exam to draw a Nyquist plot, so you can draw, something that is normal for second order system, and the inverse then looks like a fish. Okay, how do you indicate your stability margins? SM and RM are the terms that we have already discussed as well. So I'm expecting you guys to remember that. Okay, so next, this is really where the mathematical stuff is going to come in. All right, but don't worry, we'll do this step by step. Okay, so let me just cover up in case you guys get overly worried. Okay, so for performance robustness, understand that we studied a few sensitivity functions and transfer function, which is called S. Okay, that relates your disturbance to output. Okay, so if S is large, your effect of disturbance on the output is large. T relates measurement noise and output. Okay, so if T is large, measurement noise is amplified in the output. SU, which is your control sensitivity function that relates to how large your plant capacity can be. TF, simple transfer function for closed loop, that relates your filtered response to your output. And TF is very, very close to T. Actually, it's equals to T. Okay? And the other thing is we have said that SU is T times T divided by T. Alright, so SU is related to T. And the transfer function is also related to T. Alright, so why do I even bother looking at so many? I just look at S and T. Enough. Okay, so we only need to consider the effects of perturbations on S and T. Alright, so how robust is our system? Just look at S and T. Okay, so if our system fresh out of the factory was initially L0, that's the nominal loop, after 10 years down the road, it became L. Okay? Your S naught, which is really L, 1 over 1 plus L, is now S. Okay, S naught, which was 1 over 1 plus L naught, is now S. That's 1 over 1 plus L. T naught was L naught over 1 plus L naught. Over time, 10 years down the road, it became T. Okay, which is L over 1 plus L. And your inverse loop gain, similarly, which was 1 over L naught, 10 years down the road is now 1 over L. So how do I analyze as to whether 10 years down the road, my system is still robust or not? Okay, so this is what I'm going to do. I wrote here, page 13, part 2 of feedback notes, so you might want to write that down. Okay, if you don't understand, you might, go back to your notes and have a read. I think with my past experience, everybody seems to understand my lecture, so it should be okay. But anyway, all right. Okay, so ignore all of this. Let me just tell you now that we are going to show you how relative changes in S naught due to a change in your plant, P naught, 10 years down the road equals to minus T naught. Okay? I'm also going to show you that we can prove that the relative change in T naught due to a change in P naught 10 years down the road is equals to S naught. Okay? All right, and you can also observe the same for the inverse condition. Okay, so you might want to write that down first. All right, so we can observe the same for the inverse condition, which says that the relative change in 1 over S naught due to change in 1 over L naught is also minus T naught. Okay, and the relative change in 1 over L naught, 1 over T naught due to a change in 1 over L naught is also S naught. Okay, so it's the same. Whether you look at S naught or you look at 1 over S naught, you look at T naught or you look at 1 over T naught. Okay, if the plant changes, all right, the change in S naught due to P naught is minus T naught. The change in 1 over S naught due to 1 over, I wrote L naught here, but L naught is P naught, really. Okay, is minus T naught. Okay, all right, so the relationship is the same. All right, okay, so how do you see that? You look at this group of equations on top, you can actually try to observe that. All right, so if you look at the equation on top, if there is a change from 1 over S naught to 1 over S, all right, if there's a change from 1 over S naught to 1 over S, that gives you a difference, which is really simply 1 over S minus 1 over S naught. Okay, and then we like to normalize. So we normalize by 1 over S naught. All right, you can prove it mathematically. I've done the proving again this morning just to make sure it's correct. You can show that this is T naught times 1 over L naught minus 1 over L over 1 over L. All right, and this is not really the difference between 1 over L naught and 1 over L, because the difference you are looking for is 1 over L minus 1 over L naught. Okay, over 1 over L. And there should exist a negative sign. Okay, if you look at it that way. All right, and if you look into the other equation, which is if your 1 over T naught has been perturbed to 1 over T. So the difference is 1 over T minus 1 over T naught. And then you normalize that. Okay, you can equivalently prove that this is S naught times the delta change from 1 over L naught to 1 over L. All right, and the relationship is S naught. Okay, since the equations are written for you here for these two conditions, I'm not going to go through them in detail, but I'm going to go through this part. Okay, so this part has a relatively high heat rate. Heat rate, yes. Okay, so if you go through in terms of the concepts that we can test you for control for, we like to understand how well you know perturbations. How well do you understand robustness? Okay, so the whole thing is really talking about 10 years down the road when your plant has changed. Okay, how robust is your control design with respect to the sensitivity function and the complementary sensitivity function. Okay, and then how does it relate to what you know now? Okay, so I'm going to prove this. Let me just take this away. Okay, nobody is screaming. Very good. All right, so this is what I'm talking about. Okay, if you have a piece of paper, I encourage you to try to follow what I'm saying. Okay, so basically, what we covered so far in our lecture is this. We said that the control sensitivity function SU is C over 1 plus Cp naught. Okay, and the other function that we learned that says performance of our system, which is really the output over our reference input, and that is T times F. Okay, and this T is none other than Cp naught over 1 plus Cp naught times your filter F. And these two functions are related to your sensitivity function. The nominal sensitivity is S naught, which is 1 over 1 plus Cp naught. Okay, and this is really just 1 plus Cp naught inverse. Okay, and these two are also related to your complementary sensitivity, the nominal T naught, which is Cp naught over 1 plus Cp naught. Okay, so rewrite it. This is just Cp naught times 1 plus Cp naught inverse. Okay, all right, and we say that it's good enough just to look at these two because they are all related. All right, and what we want to understand is, you as a control designer is going to give us a C here that works with a nominal system P naught out of the factory. Okay, so day one out of the factory is P naught. So after 10 years, how robust is your design in terms of the sensitivity and the complementary sensitivity? Because S naught and T naught relates to your stability margins, SM and RM. Okay, how robust are these 10 years down the road? So what is the relative change in S naught due to the relative change in P naught? What is it? If your plant has changed 10 years down the road, what is the equivalent change on S naught now? And what is the relationship? Okay, so we are interested to find out, right? All right, so what we do here is we say that I'm going to take the delta of my S naught over S naught. I'm going to take the delta of my P naught over P naught. Relative change over relative change. All right, so this is going to give me delta S naught over delta P naught. All right, times P naught over S naught. Okay? All right, and what do you see here? So basically what you're going to do now is differentiate S naught with respect to P naught. And then just multiply this to P naught over S naught. Okay? What is S naught? S naught is 1 plus Cp naught inverse. So differentiate. Differentiate something like this with respect to P naught. Can you all do this? You have 1 plus Cp naught bracket to the power minus 1. So I'm going to differentiate this with respect to P naught. Bring the minus 1 down. Okay, and then you differentiate. You change this to minus 2, and then you differentiate whatever that has a P naught inside, right? You multiply that with C. Very good. So you have minus 1 plus Cp naught to the power minus 2. Okay, and then times C. Alright, so now your brain is starting to work. And then the next thing it says, okay, multiply by P naught. Okay, and then next thing you say, okay, divide by S naught. What is S naught? S naught is 1 over 1 plus Cp naught. So divide by S naught means I multiply by 1 plus Cp naught. Okay? Alright, so you have 1 plus Cp naught, you have 1 plus Cp naught to the power minus 2. So that gives you negative 1 plus Cp naught at the bottom. Okay, and then for the numerator, you have C times P naught. So this is Cp naught. And what is this? What is this equal to? It's equal to minus T naught. Very good. Okay, so there you go. You have proven that a relative change in S naught due to a relative change in P naught is minus T naught. Okay? What happens to the other sensitivity function that we're interested here, which is the T naught value? So when we test you the concept, we seldom test you half the concept. Okay? We always test you the whole concept. So you also have to tell us what happens to the complementary sensitivity function. Okay, so we want to know what happens when there's a relative change in T naught due to a relative change in P naught. Okay, so you expect that, yeah, now I know already. Okay, I just do the same thing now. I change my S naught to T naught. Okay, yes, that's correct. So let us just write that down. So it's just delta T naught over T naught over delta P naught over P naught. Okay, so rewrite it a little bit so that it looks nicer, easier to understand. All right, and the next thing is, of course, you have to prove, you know, what this is. And we can do this in two ways. One is, of course, you know, I think you can go home and do it yourself. Or we can go through and then you still go home and then practice again yourself. Yeah? Okay, so if you have T naught, all right, which is Cp naught over here, over 1 plus Cp naught. So this is Cp naught times 1 plus Cp naught with the inverse. So there are two functions here. How do you differentiate a product of two functions? Product rule. Okay, so you keep one and then you differentiate the other, and then you keep the other and differentiate. Okay, so let's say we want to keep Cp naught first. So you keep Cp naught, and then you try to differentiate this, which will give you 1 plus Cp naught bracket square. Okay, and that's a function of Cp naught inside, so this is just minus C. Okay, and then plus, you keep the other, so automatically is 1 plus Cp naught at the bottom, that's what you keep, and you differentiate Cp naught, so that gives you C. Alright, don't forget that you still have a P naught over T naught over here. Okay, next thing then becomes very simple, which is to simplify. Okay, and how do you simplify this? So here, you can work it out. You will have minus C square P naught. You give them the same denominator. So 1 plus Cp naught bracket square, and then plus C on top. So C times 1 plus Cp naught. Okay, and you see that, well, I have a C square P naught, I have another C square P naught. Cancel, cancel. Okay, and I end up with just C over 1 plus Cp naught bracket square. Okay? And what is this? How does it relate to anything that we know? Okay, so the next thing I'm going to do is I'm going to tell you that, of course, oops, I've forgotten this. When I said that we shouldn't forget that. Okay, so you have another P naught over T naught. So that's going to give you P naught over T naught is 1 plus Cp naught over Cp naught. Okay, and that allows you to simply cancel the square here, cancel this part, cancel the C, cancel the C, cancel the P naught, cancel the P naught, and you end up with 1 over 1 plus Cp naught. And that is just S naught. Okay, so the relative change in T naught due to a relative change in P naught is S naught. Okay? Alright, so how do I know whether 10 years down the road, when my plant has changed, what is the effect on my sensitivity function and my complementary sensitivity function? All I need to do now is to analyze what is my T naught and my S naught. Okay, to see if it causes any bad effects here. Alright? Okay? So, everybody is done? Alright, so this is what we are saying here, that at the bottom of the slides we have written down. That a relative change in S naught due to a relative change in P naught is minus T naught. Alright, and a relative change in T naught due to a relative change in P naught is S naught. Okay, and the other thing that you notice is, okay, alright, so what's the big deal? Okay, what can I make out of this? Alright, the thing that you know is, of course, you know that S is small and low frequency. Alright, so if S is small and low frequency, it means that, you know, the relative change in P naught, due to a relative change in P naught is related to S. And S is small and low frequency. So at low frequency, T is very, very robust. Because no matter how P naught changes, you don't get a very large delta T naught. Okay? When you have a delta P naught, alright, you don't get a very big delta T naught because they are related by S naught, and S naught is very small and low frequency. Okay, so your T is robust at low frequency, and that's fantastic because low frequency is where you have large T. It's where you get your perfect command tracking response. Okay, because at low frequency your T is 1. Alright, conversely, T is small at high frequency. So if you look at this, okay, so the change in S naught that I can expect when my plant changes is minus T naught. And at high frequency, my T naught is very small. Oh, so my S is very robust at high frequency. Because at high frequency, when my plant changes, S doesn't change much. And this is perfect because I'm interested in S at high frequency. At high frequency, my S is very high. Okay, so it all works very well. I'm happy with this. Okay? Alright, so this is how you can ensure that, you know, if you follow what we have taught you here, your control system is guaranteed to be robust 10 years down the road. Alright? If you're not going to be a control designer, at least you can tell the control designer, hey, I know how you can make your control system robust. Don't blame it on my mechanical hardware. Alright? Okay? So if everybody is on the same page, let's just wrap this up very quickly. So a quick reminder, why is this important? This is important because your sensitivity and complementary sensitivity functions are related to your stability margins, SM and RM. Okay? Alright, it's also important because, you know, if you look at the review of design requirements, alright, so you have just realized that if you look into your sensitivity function, it's small and low frequency. You look into your complementary sensitivity function, is small and high frequency. Alright? And S, if it's small and low frequency, of course, it attenuates disturbance because Y equals to S times D. Well, it then gives you, of course, good command response because you don't have the problem of disturbance. And at low frequency, your T is 1. And Y equals to T times FR, so of course the command response is good. And you know that delta S naught over delta P naught is minus T naught. Alright, so it's small and low frequency, and that also gives you robustness of T at low frequency. Alright? Okay, and the complementary sensitivity is small at high frequency, basically to prevent really your SU from being very high, because T is SU over P. Alright, it also prevents adverse effects, the very bad effects of measurement noise, because y equals to minus t times n. All right. It also prevents the loss of robustness in your S at high frequency, because delta T naught over delta P naught is S naught. All right. Okay. So when T is very small at high frequency, your S stays robust. It doesn't lose the robustness. Actually, I shouldn't write it like this. I should swap these two. Because this relates to this, and this relates to this. Okay? All right, and then done with low frequencies, done with high frequencies. That's also what we call crossover region. So in between, when your loop gain is approximately 1, we want to really avoid the peaking of S and T, so that we don't have very large S that results in large disturbance attenuation. We don't result in very large T that results in excessive influence of measurement noise. And we don't lose our robustness in both S and T. Okay? So that's what we don't like. Okay? Alright, so not too bad, right? You guys should still be able to follow. We have another 1, 2, 3 slides, simple slides before we do revision. But I think we should go for a break first. Okay, so let me just finish the 3 slides. I'll take this away. Okay. Alright, so quick recap. We talk about loop gain, which is L, and L is C times P. So this is one of the very, very important block diagram that you should know. And now in control 4, we are studying a 2-degree of freedom system. 2 degrees because you can control F, that's the filter, and control the controller C. That's why it's called 2-degree of freedom system. There are 3 inputs. There's the reference R, disturbance noise, and measurement noise that arise from very bad sensors. Okay, and basically your loop now is CP naught. So L is CP naught. And performance and robustness results in specifications on sensitivity and complementary sensitivity functions. That's the S and your T. Okay? And of course, if you have bounds, if you have conditions on your S and your T, what is S and T made of? It's made from L. It came from L. So if there's a bound they're going to put on the S and the T, it results in bounds on your loop gain L. Okay, so just understand that. So this brings us to the next point that we really need to shape our loop. All right, so for the loop L, J omega, across a range of omega, it has different magnitudes and different phases. Okay, and we know that for at least first order systems, when you have a low frequency, you have a large loop gain, and at high frequencies you have a small loop gain. And corresponding, there is also bounds for your loop gain due to the bounds on your S and your T. Okay? Alright? And the other thing to observe is, in between, there's this what we call a crossover region. Alright? Where here, really, you want to try to constrain your phase as well, because you want to make sure that it's still stable. Alright, so we're not going to go into too much depth. Just understand that because you have bounds on S and T, you end up with bounds on L. Alright? Okay? And the last slide that we are going to do before we go for a break is a little bit more detail on why we are so concerned with the crossover region. Alright, so where is the crossover region? It's the region where L is approximately 1. And we understand from Nyquist stability criterion that the more closely L approaches -1, the more S will peak. Because when you approach -1, your vector margin, that's SM, becomes very small. Okay, SM is the minimum distance from -1 to the point on the Nyquist plot. So when the Nyquist plot is close to -1, SM becomes very small, and SM is 1 over the max of S. So S peaks when SM is very small. Okay, so similarly, if L approaches minus 1, your inverse loop, 1 over L approaches minus 1 as well. And then your Rm, which is the inverse vector margin, Rm becomes very small. Okay, and Rm is 1 over max of T. So the more closely 1 over L approaches minus 1, typo here. The more closely 1 over L approaches minus 1, the more T will peak. Alright, because Rm is 1 over the max of T. All of you are required to know how to prove this. Okay? Because you have done it in our lectures. Alright, so to avoid peaking, we need very good stability margins in Sm and Rm. Okay, but of course, as we covered just now, you need to also ensure on your own that there's a constraint in the gain and phase. Alright? And of course, there are also stability margins for gain and phase. Okay, just understand that. Alright, so that's the end of this part of the lecture. Alright, let's take a break. So it's now 12 o'clock, we come back about 12:15. Okay, so you guys can go and get some snacks if you want to. Okay, I'm not sure if those who went to the canteen have really come back. But it's okay because every time at the beginning of the lecture and especially after the break, I would go through a little bit of recap, stuff that get you guys to calm down. Okay, so if you go through the resources in Moodle, alright, you will see this, which is a stack of practice questions. Alright, so these are very common to what you will see in terms of the concepts that you should know, and those that are really what we can actually test your understanding on. Okay, so if you turn to the last page, alright, you will see this particular question. 10. Okay, you should have no issues with question 8, which is talking about gain margin and phase margin. Okay, that we assume that you know, we have gone through that as well. So do this as practice. Alright, so this has about maybe, I think, 30% hit rate. Question 10 is something that is very, very familiar to us. Okay, so you guys should be able to do this with one eye closed now. By week 10, maybe 2 eyes closed. Okay, so what it says is, derive the closed loop equation relating y to r, d, and n. Alright, derive. So you should do the derivation and show us that y is cp naught over 1 plus cp naught fr plus 1 over 1 plus cp naught d minus cp naught over 1 plus cp naught n. Okay? And then B says define sensitivity function S and complementary sensitivity function T naught in terms of CMP. So after you have part A, you can then tell us that, oh, this is S naught and this is T naught. Okay? That's how you define. So you tell me that S naught is this, equals to 1 over 1 plus Cp naught, T naught equals to Cp naught over 1 plus Cp naught. Sketch the plots. Then you just draw the plots for me. Whether it's on dB scale or not on dB scale. So if it's not on dB scale, then this is 1 and 1 here. If it's on dB scale, then it's 0 dB and 0 dB here. Alright, and this is based on the assumption that the plant has a low pass characteristics. So this is your simple first order low pass system. And that gives you a plot like this. Okay, and then explain how this has resulted in the trade-off in achievement of key feedback design goals. So what's the trade-off? So just tell us that, obviously from this plot, and from the equations, S naught plus T naught equals to 1. So they cannot be small at the same time. Okay, and you want to avoid PT in S and T naught, because S amplifies the effect of disturbance on the output Y. T amplifies the effect of measurement noise on the output Y. And what do you want to achieve? You want to achieve good command response. So what is good command response? You want your Y to follow your filtered reference. Okay, you want Y to follow your filtered reference. So you want T to be 1, because then Y equals to FR. But you don't want any of your disturbance or any of your measurement noise inside. Okay, that's what you want to achieve end of the day. You want Y to follow FR. Okay? So far so doable, right? And then part C, easy now. Show that the following constraint holds. S naught plus T naught equals to 1. So just write down for us. S naught is 1 over 1 plus P naught plus CP naught over 1 plus P naught equals to 1. Okay? Write enough so that we don't think that you copied this for somebody. Okay? Alright, when we say define or derive or prove, right, give us enough steps. Alright, so we know that you really know what you're talking about. Discuss the implications of this constraint. So they cannot be both low at the same time, and you don't want them to peak as well. You know, talk about this constraint. D is what we just said in the lecture. Show that T naught is equivalent to relative change in S naught, which result from relative change in P naught. We are very kind. We tell you that show us that T naught is minus delta S naught over delta P naught over P. Okay, so just prove what we have proven in the lecture just now. Similarly, give us enough steps in between, so we don't think that you just tikam, guess only. Okay, if you just write down that delta S naught over delta P naught over P naught equals to minus T naught. You get 0 because that's not proving. Give us enough steps in between, alright? Okay? So this can be, how much can this part be? This part can be 5 marks. Because there's a significance. What is the significance of this result? So you tell us that, well, if this is true, then your S naught is very robust to perturbations in P naught at high frequencies. Why? Because a high frequency P naught is very small. Alright, so if there's a change in P, so if there's a delta P naught times P naught, which is very small, it gives you very small change in S naught. Okay, so your S naught is very robust at high frequency because delta S naught over delta P naught is T naught minus T naught. Just tell us this. Okay, so this is how we can test how well you understand the concepts. Okay? Alright? Not too bad, huh? Alright, so if you are keen to find more questions to practice, this first part of Control 4, please go through the past year exam papers. There was a slight change in the format last year, so we actually have a section A which is compulsory, and if you look at last year's question paper, there are some small questions that we gave in section A and it's compulsory, so you cannot run away from that. So you must know like basic things, small calculations, small things all of this small stuff that tests how well you understand Control 4. Okay? Alright, so far so good. I said that we will do a recap, a revision. Yep, okay, there it is. Okay, so before I move on to the next section, that is about, now that you understand that you need a proper controller C, because C affects your S naught, it affects your T naught, right? So how do you design the C, and what does C look like? Okay, so that's the next section that we're going to talk about, which is about designing a PID controller C. But before we go there, let me just quickly bring you through what we have discussed so far. No need to copy this, because it's all in your notes. Alright, so understand that we are looking at a general system, okay, with a reference R, a disturbance D, a measurement noise N, output Y, control output signal U. So the question might come in and say that, define the input and output variables of the system in figure 1. So just tell me R is reference, D is disturbance, N is measurement noise, Y is output, U is control output. Okay, and you get maybe like 2 marks or 3 marks. Okay, next question, derive the output Y with respect to the input signals R, D, and N. So just write down this for me. You don't have to memorize, because if you know how to cover up and then find a closed loop transfer function, you can actually produce this and this. But if you really cannot, then at least you help yourself a little bit. All right. Okay. And then there's also the control sensitivity function SU, which relates the output U and the input, which is the error E. Okay. So you're looking at U and the relationship between U and E. Okay, what is E? E is the filtered reference minus measurement noise minus output Y. Do you minus D? No, why? Why do you not minus D? D is already inside your Y. Huh? D is already captured inside your Y. Alright, so there's no need to minus D. So it's just FR minus. Sorry. See? Alright, okay. What did we prove? Oh, sorry. So this is sorry. Okay, so it's F1 minus M as we have proven this. Okay, so that was when we first started off to say U equals to C times E, and E is FR minus N minus Y, and then if you to prove that, you end up with U equals to SU times FR minus N minus D. Alright, okay, so even I make mistakes. Okay, alright, so these are the transfer functions. And then we learned that, for low pass, simple first order transfer function, this is a relationship of loop gain. And at low frequency, loop gain is larger than 1, high frequency is lesser than 1. There's also a crossover frequency, which is approximately 1. And in this crossover, we say that neither the sensitivity or the complementary can be small. So it's crucial, it's very important to ensure that you have your one peaking in S and T. Why? Because if your S peaks, you amplify disturbance. Y equals to F times D. If your T peaks, you amplify measurement noise. Okay, Y equals to minus T times N. Okay, the other thing is, of course, you don't want peaking in S and T. You need to keep your Nyquist plot L and 1 over L away from minus 1. Because if L is close to minus 1, your vector margin, Sm, is very small. And Sm is 1 over S. And then S will be very large. If 1 over L is close to minus 1, your inverse vector margin, Rm, is then very small. And Rm is 1 over T. And then T becomes very large. Okay? What does S and T look like? They look like this. Okay, so S is small at low frequency, which is where you get good disturbance attenuation. T is small at high frequency, where you get good measurement noise reduction. At low frequency, between omega equals 0 to the bandwidth B, this is where you get good command response. And of course, you also need low noise sensors, because T is high. Okay, in your bandwidth region. Alright? Okay? We have covered all of this. Alright, the other thing that we also spoke about is what happens if 10 years down the road, your plant has changed. Okay, fresh out of the factory, it was P naught was 1 over S plus 1. 10 years down the road, now your P is 1 over 1.2 S plus 1. There's a longer time lag. Alright, so is your stability and robustness analysis with S naught and T naught still valid? Now that your P has changed. Okay, so this question really relates to what we have proven just now, that you know, I know that if there's a change in plan, and this change in plan creates a change in S naught, and this is related to minus T naught, and T naught is very low at high frequency. Okay, so this means that S naught is very robust at high frequency, which also happens to be the region where S naught is significant because S naught peaks at high frequency. So that's fine, it's okay. All right, and the other thing is, of course, if I look at T naught, the delta change of T naught over changes in the plant is related to S naught. Oh, and S naught is very low at low frequency, okay? So my T naught is very robust because when plant changes, my T naught doesn't change so much. Okay, the delta change in T naught is you take the delta change in your plant times S naught. Okay, so S naught is very small, all right, at low frequency. So T naught is very robust at low frequency, which is good because your T naught is only significant at low frequency. All right, so that's fine. If you follow what we have taught you, 10 years down the road, when your plant changes, your analysis is still robust. All right, okay? The other thing before you forget, this has been tested before as well, Dawes criterion. So the question might come in as, what's the necessary and sufficient condition for closed loop stability? The key word is necessary and sufficient. All right, so you must tell us that, you know, if you look at the loop perturbation, you know, the difference between your nominal loop and your actual loop is L minus L naught, and you normalize by L naught. This thing must be less than your SM. The loop perturbation, which is L minus L naught, must be less than SM. And what's SM? SM is the magnitude of 1 plus L naught. Okay? So it's 1 plus L naught, you normalize the left hand side by L, divide by L naught, the right hand side also divide by L naught. So if you can get to this step, what is this? This is 1 over T naught. Alright, then the next thing you tell us is let this be much lesser than W1. W1 is just a very big circle. You draw around this entire 1 over T naught for a range of omega frequency. And then this close to stable if and only if your W1 is strictly lesser than 1 over T. This is half the solution. Where is the other half of the solution going to come from? Is to tell us that similarly, if there is a change in the inverse loop, so instead of 1 over L naught, now it became 1 over L. This perturbation, the difference in the inverse loop must be less than Rm. What is Rm? R is the inverse vector margin. That's the minimum distance from minus 1 to the inverse loop 1 over L naught. And Rm is the magnitude of 1 plus 1 over L naught for a range of frequency omega. You normalize the left hand side and the right hand side by dividing throughout by 1 over L naught, and the right hand side gives you just 1 over S naught. Similarly, this is closed loop stable if and only if you draw a very big circle called W2 around all of 1 over S for a whole range of frequency omega. Alright, and W2 is much strictly lesser than 1 over S. Okay, so that's the Dawes criterion. When it was tested, this was 13 marks. Alright, in a 20 or 25 mark question. Alright, okay, the next thing that we cover, I'm not going to cover this again, is how you relate your vector margins, SM and RM, to your sensitivity functions S and T. Okay, and last but not the least, we talk about robustness. Okay, so you guys should know how to derive this by now. Alright, how robust is your analysis when there's a change in plant? Okay, so all okay, alright, if this is tested, maybe it's about 5 marks only. Okay, so if there are no questions, I'm just going to point out to you that for the next section, called PID controller design, there is a stack of text in Moodle, which you are encouraged to read. Alright, go through on your own. Okay, but we will cover some parts of this in the slides. Alright, okay. It's now 12:35. So I plan to cover a little bit of introduction, And then next lecture, when I come back, I will recap a little bit of introduction and we'll go on to calculation. So now let's just listen. There's no calculation required. Okay, so you guys may not have the notes, I think, if you are not prepared for this. Okay, so where are we? We are on chapter 8, called PID controller design. We have spoken a lot about shaping the loop. You shape L, which is CP. And what is L? L is C times P. Okay, so what is C? If C is a PID controller, then we have to actually learn how to design your PID controller such that you reach your design targets. And what are those? Those are disturbance attenuation, good command response, robustness with respect to stability and performance. Okay? So we want to learn how to modify the shape of the loop to achieve what you desire. And what are these targets? These targets are similar, are they equivalently translated into requirements for your S and your T. Okay, so before we go to that part, let's just look at what stability is as a revision. Alright, so if this is a typical Nyquist plot, again, you guys, although we didn't go through the calculation in detail, but I expected to know how to calculate gain margin and phase margin and stability margin. Okay, so from this plot here, alright, you can see that the critical point is over here. -1 is over here. Alright, this is the critical point. And the one that is in dotted line is your unit circle. So everywhere the unit circle has a magnitude of 1. Okay? In this third order transfer function, it crosses the negative axis over here. Alright, that is what we call this frequency, we call it omega m, gain crossover frequency. But this is actually very, very far away from the critical point. Alright, so what is the gain margin here? Almost close to infinity. It's about 53.8 dB. How do you calculate the phase margin? You look at the Nyquist plot and its intersection with the unit circle. So this point here, omega c, is what I call phase crossover frequency. And here, if you take a protractor, you can measure that the angle from this point to the negative rear axis is about 64. Why is it 84? Should be about 60, maybe at most 64.1. So this 6, because 84 will be about close to 90 degrees already. 64.1 degrees, okay? And there is the equivalent delay margin. So you have to know how to convert the phase margin into a delay margin at that particular frequency of 0.101 radian per second. Okay, so you have to know the relationship. I'm hoping that you know how to do this, but I'm not very sure. So let me just show you this once. Okay, so how do you read the gain margin? And how do you convert phase margin to delay? Alright, this is a Boolean plot. So you look at this plot, there's a magnitude and a phase. Alright, and we said that if you look at the Nyquist plot, the intersection of the Nyquist plot with the negative rear axis is at frequency omega m, gain crossover. Alright, so if you look at this, this is where your Nyquist plot touches the negative rear axis. And the negative rear axis is at phase of -180 degrees. Alright, so you take 180, cuts your phase plot. This particular frequency is your gain crossover frequency, or omega m. Okay, and how far is your intersection of the negative rear axis away from the -1 point? So -1 point in dB is 0. So how far is it away? Is 53.8 dB away. That's your gain margin. Alright, how much is 53.8 dB? So you need to tell me what's the raw number. how much more gain can you multiply your closed loop system by before it becomes unstable. So just convert 53.8 dB into 20 log base 10 gain margin. So what's gain margin? Gain margin price of calculator is 490. This can be 2 marks, right? What is phase margin? So phase margin is when your Nyquist plot cuts your unit circle. So unit circle has a magnitude of 1, which is 0 dB. So dot 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 dot, cut your magnetic plot. This is your omega c, phase crossover frequency. Pull it down. How far are you away from the minus 180 degrees? So this is 5, which is your phase margin. Is why it's 84.1 degrees. Very strange, huh? Okay, so anyway, that's why it's written here. So 84.1 degrees, how much is this? How much extra phase can you add to your system? You don't actually add phase to your system. You add time delay to your system, time lag. Okay, so how much additional time delay can you add to your system before it becomes unstable? So converting this into an equivalent time delay at that particular frequency, 0.101. So if omega c is 0.101 radian per second, frequency fc is omega c over 2 pi. That gives you 0.0161 hertz. And you have 84.1 degrees at 0.0161 hertz. So you convert, you normalize the degree, so 84.1 degree divided by 360 degree times the time period. Because 360 degrees is one entire time period. So what's your time period? Time period is 1 divided by your frequency. 1 over 0.0161 hertz will give you seconds. Alright, so you have degrees over degrees times seconds. So that will give you 14.5 seconds. Okay, this can be another 2 marks. Alright, in your section A. Okay? Alright? Okay, so back to what we want to learn about PID controller. I'm just going to stop here because I'm going to recap on this next week. So what is a PID controller? A PID controller is different from what you learn in control 3. On control 3, you only learn P, proportional. You touch a little bit that, okay, I know that I must have an integrator. There is zero steady state error, but I'm not quite sure why. Okay, so understand that in this part of the course, we are looking at CS. Okay, where CS is a PID controller, and it comes with a proportional gain K, which is a pure number, an integral gain Ki, which is Ki over S, a differential gain Kd, which is Kd times S. How did this come about? This came about because in a PID controller, we are taking the error that is fed into the controller and producing an output called U. And what is U? U is a proportional gain, Kp, times the error. Alright? Plus a gain, Ki, integral gain, times an integration of the error. So if you have error, you are going to sum up the error, multiplied by Kd. Alright? Plus a different derivative gain, Kd, multiplied by the derivative of the error, E dot. So if the error comes in as very noisy, you're going to take all of this noise, okay, which is the delta E across delta T, that is your E dot, and you're going to take all of these changes in the gradient of your error multiplied by Kd. So what do they do? So first of all, I think, oh, I'm going to sum up my error. So Ki can help me to fix the problem when errors accumulate over time. Yes? Yeah. I think Kd, what can Kd do? Kd can potentially help me fix the problem of high frequency noises in my error because it works on E dot. Yeah? And what does Kp do? Kp will just work on the amplitude, the magnitude of the error. Okay, so we'll look into this a lot more next week. Okay, and exactly how you should design your Kp, Ki, and Kd for PID control. Okay, so may I have my attendance list back, and I'll see you guys next week.
Damn, you guys are fuss.